Hello everyone, welcome to SJC content. So this is Dr.L.Jethruth, Emelda Mary, Assistant Professor in Mathematics, St.Joseph College of Arts and Science, Autonomous, Cuddalore, Tamil Nadu. In this video lecture, I am going to explain about connectivity in graph theory for second BSc Mathematics. So first let us define what is connected or disconnected. A connected graph is nothing but if there exists a path between every pair of vertices, then the graph is said to be connected. If not, it is called disconnected. Then what is connectivity? Connectivity means by removal of a vertex, the minimum number of vertices are removed from the graph. Then the resultant graph is disconnected means, or if it has more than one component means, then the number of vertices is called connectivity. So the definition is given like this. A subset V dash of a vertex set V of a connected graph G is nothing but a vertex cut of G if G minus V dash is disconnected. Suppose the number of vertices in the subset V dash is K means, then it is called K vertex cut, or you can say that the connectivity of G is K or G as K connectivity. Here V dash is called also known as the separating set of vertices of G. A vertex V of G is a cut vertex of G if G minus V is disconnected. The next definition. Let G be a non-trivial connected graph with vertex set V of G and S is non-empty subset of V of G, and define S dash equal to V minus S. Let us denote S dash comma S is the set of all edges of G that have one end vertex in S and other end in S dash. Then the set of edges of G induced by S dash and S is called edge cut of G. Or you say that is an edge E is a cut edge of G if G minus E is disconnected. If the cardinality of the edge cut set is K, then it is called a K edge cut of G. So in these two definitions, you clearly understand that there are two connectivity. One is called vertex connectivity and another one is called edge connectivity. By removal of minimum number of vertices, makes the graph to be disconnected, means that is called vertex connectivity. The cardinal is vertex connectivity. If the cardinalities of the minimal vertex cut is K, means that is, then the graph is called K vertex connectivity, or the connectivity is K. The same definition is applicable for edge connectivity. Okay. So based on this, we have a theorem. A vertex B of a connected graph G with at least 3 vertices is a cut vertex of G if and only if there exists a vertices U1B or U1W of G distinct from B such that V is on every UW path in G. This is a very important theorem. This theorem says, suppose G is connected and it has 3 vertices as a cut vertices means, then definitely there exists UV path which is distinct from the third vertex. That distinct path vertex will always lies in that path. Okay. So see the proof now. Suppose I assume V is a cut vertex of G. What is called cut vertex? If I remove a vertex from G, then the graph is disconnected, means then that vertex is known as cut vertex. Here I assume that V is a cut vertex. Definitely G minus V is disconnected. Therefore, G minus V disconnected means definitely it has more than one component, says G1 and G2. Take U belongs to V of G1 and W belongs to V of G2. That is, U is a vertex belongs to the first graph G1 and W belongs to another graph G2, the vertex set of G2. Then every UW path in G must contain V. Every UW path in G must contain V if V is the internal vertex of UW path. Otherwise, U and W would belong to the same component of G minus V. So conversely, assume that the condition of the theorem is holds good. Then the deletion of a vertex definitely destroys every UW path in G. Hence U and W will belongs to distinct component of G minus V. Therefore G minus V is disconnected. Hence V must be a cut vertex of G. The next theorem is an edge E is equal to xy of a connected graph G is a cut edge of G if and only if E belongs to no cycle of G. Let us take edge. Let us define edge E is equal to xy. We call it as a cut edge of G. So cut edge means G minus E is disconnected. Okay, and define a set S dash and S, that is collection of all edges, which is a partition of a edge set of G. Then define G minus E so that one of X and Y belongs to S and other to S dash. Say X belongs to S and Y belongs to S dash. If E belongs to a cycle of G, then S dash comma S must contain at least one more edge, which is a contradiction, that S dash comma S is equal to singleton E. Hence E is not on any cycle of G. So conversely, assume that E is not a cut edge of G. Then G minus E is connected. Hence there exists XY path in G minus E. Therefore P union of singleton E always leads to a cycle in G containing E. Hence the proof. Next we have another theorem. An edge E is equal to xy is a cut edge of G. What is G is a connected graph if and only if there exists a vertices U and V such that E belongs to every UV path in G. This is the immediate what is called, you can call it as a previous theorem, the result of the previous theorem. In case I define edge E is equal to cut edge of G, then G minus E has two components, say G1 and G2. If I take U belongs to V of G1 and V belongs to V of G2, then clearly every UV path in G contains as edge E. Conversely, suppose that there exists vertices U and V satisfying this condition of the theorem, then there exists no UV path in G minus V. Therefore, G minus E is disconnected. Hence, E is a cut edge of G by definition of a cut edge. Next is a connected graph G with at least two vertices contains at least two vertices or cut vertices or not cut vertices. Suppose that n of G, number of vertices of G is greater than or equal to 3. Let U and V be two vertices of G such that the distance between UV is maximum. That means d of uv means the length of the shortest path. But here I am assuming that the distance between uv is maximum. The shortest length of the path is maximum. To prove that neither u nor v is a cut vertex of G. For that, I assume that u is a cut vertex of G. Then, if u is a cut vertex, definitely G minus u will be disconnected. Therefore, G has two components, G1 and G2. Take the vertex set V. Vertex V belongs to V of G1, W belongs to V of G2. Then every VW path in G must contain U. Consequently, the distance between V and W is greater than or equal to the distance between V and U. So which is a contradiction of choice of U and V. Hence U is not a cut vertex of G because we assume that D of UV is maximum. But we are proving that D of VW is maximum. So this is a contradiction. Hence definitely U is not a cut vertex of a G. Similarly, the same concept you can prove it for the vertex V also. Suppose V is not a cut vertex of G, and if f of n of G is greater or equal to 2, then K2 is a spanning subgraph of G. So no vertex of G is a cut vertex of G. This completes the proof of the theorem. Move to the next proposition. A simple cubic connected graph has a cut vertex if and only if it has a cut edge. So what is called a cubic graph? Cubic graph means a three regular graph. Three regular graph means a graph is said to be regular if all the minimum degree and maximum degree are same. Then it is called regular graph. If all the vertices having degree 3 means, then that is called three regular graph. So in a three regular connected graph, you have it has a cut vertex. If and only if it has a cut edge also. Okay, see the proof now. Let G have a cut vertex V1 or V0. Let V1, V2, V3 be the vertices of G that are adjacent to V0. Because every vertex of G must have a degree 3, therefore 3 vertices are adjacent to V0. So I'll define V1, V2, V3 are the adjacent vertices to V0. Consider G minus V0, which is either a 2 or 3 component. Definitely if I remove vertex V0, then the resultant graph will be disconnected. It has more than one component or 3 component. If G minus V0 has 3 component mean, then no 2 of V1, V2 and V3 can belong to the same component of G minus V0. In this case, each of V0, V1, V0, V2, V0, V3 will be a cut edge of G. Suppose that E is equal to UV is a cut edge of G, then the deletion of U results in the deletion of edge UV. Since G is a cubic graph, therefore G minus U is disconnected, which implies that U is a cut vertex of G. Hence the proof. Now we'll move to the definition. For non-trivial connected graph G having a pair of non-adjacent vertices, the minimum K for which there exists a curve vertex cut is called the vertex connectivity, or simply the connectivity of G. It is denoted by K of G or simply K, or we can call it as kappa when G is it is a connected graph. If G is a trivial or disconnected, then K of G is taken to be 0. If G contains Kn as a spanning subgraph, then the connectivity of G is taken to be n minus 1. A set of vertices or edges of a connected graph G is said to be disconnected means if its deletion results in a disconnected graph. Similarly, we have edge connectivity. The edge connectivity of a connected graph G is the smallest k for which there exists k edge cut. So edge connectivity of G is denoted by lambda of G. If lambda is the edge connectivity of a connected graph G, there exists a set of lambda edges whose deletion results in a disconnected graph, and no subset of edges of G of size less than lambda has this property. A graph G is OR connected if K of the connectivity of G is greater than or equal to OR. Also, if G is OR edge connected if the edge connectivity of G is greater than or equal to OR. So next important theorem, for any loopless connected graph G, K of G less than or equal to, that is the vertex connectivity is less than or equal to edge connectivity less than or equal to minimum degree. So this is an important theorem. So thank you for watching this video.